We're going to start chapter 5, which is on thermochemistry, and then transition into chapter 19 on thermodynamics. So, thermochemistry is basically studying chemical reactions and the change in energy, specifically that involve heat. Thermodynamics we are still going to be studying the energy, but also how energy can be transformed. In the first law of thermodynamics, it says that energy can be converted from one form to another, but it cannot be created or destroyed. So we're always going to have the same amount of energy in the world or in the universe, but it's going to just be transformed from one type to another. So for example, when we heat our home, we take chemical energy stored in natural gas and convert it into heat by burning it. For plants, they take electromagnetic energy and convert it into chemical energy, which then we can consume, digest, and turn it into kinetic energy and heat for our bodies. So when we talk about energy being transformed, we need to think about what are we actually studying. So the thing that we are studying is called the system. So generally that's a reaction or the thing that's doing the chemistry. Okay, so in this little example, we have these hydrogen and oxygen molecules that we're going to study as they react to form water. So our inside of our cylinder here is our system, and then outside, so the cylinder and the piston and everything else is our surroundings, so everything outside of that. When we think about systems, there are three types. Open systems, where heat and mass can both be exchanged, so they can leave. That's an open system. So for example, if I'm thinking about how am I going to keep my coffee, how am I going to store my coffee? So a traditional coffee mug that you might have at home, that's an open system, right? The water vapor from the coffee that's warm can leave. I could spill it and it could escape, right? And the heat's going to leave also, and that's why it's only going to stay warm for so long. In a closed system, I'm going to be able to exchange heat, so heat will be able to leave, but not the mass. So for example, getting into a better system for coffee, I might have just a coffee thermos. Overall, it's like maybe I'll get it at Target. Nothing bad about Target, but if I get a cheap thermos, then some of the heat will be able to leave, but the mass will, if the lid's on, then it's going to stay in there. An isolated system is where heat and mass is not going to be able to leave the system. So again, with the coffee example, that might be something like a Yeti cup, right? I can have my really high quality thermos that keeps the mass as well as the heat in for a very long time. So that's closer to an isolated system. When we think about energy in general, the internal energy of the system is the sum of all of the kinetic energy, Ke, and potential energy, Pe. So kinetic energy is associated with movement, vibrations, it also involves heat. Potential energy is stored energy. So many people think of in physics being at the top of a hill. You're not moving, but there's a lot of potential to get energy through movement. Or even chemical bonds are a sort of potential energy. They're stored there and then they can be used, broken down, and energy can be converted into something else. We're going to represent internal energy with the letter capital E. And generally, it's really hard to actually know E at any particular time, but it's a lot more straightforward to see how energy changes, so delta E. When we get some energy exchange, so when we see delta E, there is usually some kind of change involved with heat and work. So the relationship is that the change in internal energy is equal to the heat plus the work in that system when there's that change. So, for example, if I'm wanting to rearrange my room or rearrange the classroom, the energy that it takes to do that is not only the work that I put into moving that, so I'm applying a force over a distance as I move a table, but I'm also losing heat as well as my body warms up. So we would have to consider both of those quantities when I think about the total change in energy. When we have a gas, that work is done with pressure volume work. So the relationship is work equals negative pressure times the change in volume. So here we have a system initially. It has this volume. As the reaction happens, the volume increases. So basically what that means is, okay, if I just look at this original system, to get it to open up to increase the volume, my system has to push out against the piston and move it up. So my system is doing work on the piston. If it goes the other way and pushes down and closes it, then the piston, or the surroundings in that case, are doing work on my system. So that's kind of that nomenclature and the language we use around work. So, but we want to think about it also numerically. So if my volume is increasing, like it is in our example, then my change in volume is positive. So I'm going to have a positive value for change in volume times by that negative out front, so my work would be negative. So the system, the way that convention is, when we have positive work, then that means that the work is done on the system, okay, by the surroundings. When it's negative, then the work is done by the system. When our heat is positive, our system gained heat. When it's negative, it lost heat. And Q has to just do with the total internal energy. So in this problem, I have gases A and B in a cylinder piston arrangement, and they're going to form a solid. So if I have two gases forming a solid, just logically, you can kind of think about it. Okay, gases take up more space than solids, so my volume should go down. So my change in volume should be negative. As a reaction occurs, the system loses 1150 joules of heat. So I'm going to write down Q equals negative 1150 joules because I lost that much heat. The piston moves downward, so that means delta V equals negative. As the volume of the gas decreases under constant pressure of the atmosphere, the surroundings do 480 joules of work. So we know work is 480. We know it's negative P delta V. Now V was negative, and we have that negative up front, so the work should be positive 480 because we have the negative volume times the negative joules. So what's the change in internal energy? So delta E from our equation, we have Q and work, so the relationship using those is Q plus W. So we have negative 1150 joules plus a positive 480 joules. Solve for that, and we get negative 670 joules. Okay, so now in a different problem, we have a system absorbs 140 joules, so Q of heat, so positive 140 joules, and and does 85 joules of work on the surroundings. So I think about that. My system is doing work on the surroundings, so it's pushing up, which means that delta V is going to be positive. So if I think about that, I do work equals negative P delta V, so I have a negative times a positive, so my work should be a negative. So I'll have plus negative 85. Well, I'll put that, actually work equals negative 85. So my delta E equals Q plus W, so I have positive 140 plus a negative 85 joules, and I get a positive 55 joules as my answer. In this problem, we have a little bit more steps to take, and this is going to be much more common of a type of question you might see on a free response. So I have a cylinder with a piston. It emits 430.5 joules of heat, so I'm going to write that down as I go. So it emits it, so it's negative 430 0.5 joules. The initial volume of the cylinder is 0.250 and the final volume is 0.980 liters. So I can calculate delta V, which is going to be final minus initial. So 0.980 liters minus 0.250 liters, which gives us 0.730 liters. Cool. And the piston expands against a constant pressure, so our pressure equals 1.35 atmospheres. What's the change in internal energy? So for that, I'm going to plug it in, and it's Q plus W. Now I know Q, but when I solve for W, so W, work is negative P delta V. So let's plug that in. I have negative 1.35 atmospheres times delta V 0.730 liters. So that gives me my work as negative 0.9855 liters times atmospheres. Now, my units for work or for heat are in joules, and this is liter atmospheres, so they're not the same, so we can't add them together. So luckily for us, it gives us this nice little relationship. So I'm actually going to convert. I know that 1 liter atmosphere is equal to 101.3 joules. So I can take my number I got and multiply by 101.3, and I know that my work is negative 99.8 joules. So now I can plug in delta E, which is Q, so negative 430.5 joules plus a negative 99.8 joules, and my delta E is negative 530.3 joules. So that's kind of the harder of the questions because there's a little bit more steps. Okay, so we're going to mostly talk about enthalpy. So enthalpy of a process is with the letter H. And it has to do with heat flow, especially when it's done under constant pressure. So it's basically related to heat. That's why it's used the letter H, because a lot of times it's been called the heat of a reaction. So the enthalpy is equal to the energy plus the pressure times the volume. Now, like we said before, it's hard to measure at any given point H, so we'll do the change in H here. So delta H equals, we'll do the delta of this relationship. So what ends up being done is we're going to put the delta into the E, the delta applied to the P, and then the delta applied to the V. And this is basically calculus. So if you're taking calculus, this is the rules specifically related to derivatives. So I believe it's in Calc 2. So if you are confused, don't worry about it. When we put those in, we get delta H equals delta E plus P delta V, and also plus a delta P times V. Now, we're doing it at constant pressure, so what happens is that delta P is 0, so that's why we don't write it there. That's why it's crossed out. So if we remember that E equals Q plus W, and W is negative P delta V, then I'm just going to plug in there. So I have delta H equals, wherever I see delta E, I'm going to write Q plus W. Now I'll have that plus P delta V. And I know work, so I'm going to plug that in now. Q equals, work is negative P delta V. And then I'm going to bring down this one, so plus P delta V. And I have a negative P delta V plus a positive P delta V, and those will cancel out. So the end result is delta H equals Q at constant pressure. So when you've thought of the terms exo and endothermic, this has to do with the enthalpy. So when delta H is positive, our heat is positive, when it's endothermic. When it's negative, it's exothermic. When we have a reaction, we're still going to think about the final minus initial, but now when we're talking about our final part of a reaction, that's our products. So the enthalpy change of our reaction is equal to the enthalpy of our products minus the enthalpy of my reactants. which is what I'm starting with. And so that delta H reaction here is for the enthalpy of a reaction. So we can see here that when we have hydrogen and oxygen reacting, those are reactants, and they have this certain energy, and water is our product, it's this energy. So if we do, our reactants have a higher energy than our products, and so our delta H is going to be negative, which is exothermic, which is why we see a big explosion. It's very exciting. Enthalpy is an extensive property, which means that it depends on how much you have. Intensive property is something like color or density, stuff like that, where it doesn't really matter how much you have of a substance, those properties are going to be the same. So density, it doesn't matter if I have 1 milliliter of water or 1,000 liters of water, the density is always 1 at 25 degrees Celsius. Or the color is of a shirt, if I have a piece of cloth, I have a big roll of it or a small roll of it, the color is the color, right? Extensive means it matters how much you have. So if I have a little bit, like a little milliliter of fuel, and if I have a big gallon of fuel, the big gallon of fuel is going to give me a lot of energy or enthalpy. Okay, so it matters how much of the substance I have. Enthalpy change for a reaction. So I'm going to just talk about this reaction up here. So if I have methane, CH4 being burned and oxygen combusting to form CO2 and water, that is an exothermic reaction. It releases 890 kilojoules of heat. Now if I reverse that reaction and I want to start with carbon dioxide and water and form methane and oxygen, well, it's the same magnitude number, but the sign changes. So if I reverse my reaction, then the sign of my enthalpy changes for that reaction. So that's where the magnitude is the same, but we'll have the opposite sign for the reverse reaction. And then the enthalpy change for a reaction does depend on the states of our reactants and products. So for example, here I have liquid water in this combustion, but if I had something like gas or solid water, then there would be a different value here. So the state does matter. So let's practice. I want to know how much heat is released when 4.5 grams of methane gas is burned at constant pressure. So I'm going to use the reaction from the last slide, where I have methane plus 2O2 goes to CO2 and 2 waters. And the delta H for this reaction from that last slide in this direction is negative 890 kilojoules. So now you're going to think of this as part of the reaction, part of the stoichiometry. It's something you can use in stoichiometry to get between moles of any of these molecules into energy, or from energy to moles or grams of one of the substances. So I'm going to start with what it gives me, 4.5 grams of methane. And I'm going to go to moles. So I'm going to use a molar mass of methane, which is 16 grams in 1 mole. Now my grams of methane cancel out, and I'm in moles of methane. Now that I'm in moles, I could use stoichiometry to get into energy. So I'm going to say moles of methane into kilojoules. So I look at my stoichiometry, there's a 1 in front of methane, and there's a negative 890 in front of kilojoules. And so I can do this math, so 4.5 divided by 16 times negative 890, so that the change in enthalpy equals negative 250 kilojoules. Or I could say 250 kilojoules were released. Now in this reaction where hydrogen peroxide decomposes into water, there's this enthalpy of the reaction. So I want you to pause and try this one on your own. Okay, so maybe pause. We have 5 grams of hydrogen peroxide. I'm going to look up the molar mass of hydrogen peroxide, which is 34 grams per mole. So the grams cancel out. Now I'm going to use now I'm in moles, so I can use molar ratio. So I'm going to go from moles of H2O2 into kilojoules for my reaction. I'm going to look at my numbers on my chemical reaction. So there's a 2 in front of the hydrogen peroxide and negative 196 kilojoules in front of my energy unit. So I'm going to do this math, and you should get negative 14.4 kilojoules, or you can say 14.4 kilojoules are released. So pay attention to the wording because that will matter. In this next bit, we're going to talk about how we could find the enthalpy using a calorimeter. So calorimetry is a process that we can use to measure the heat, specifically using a temperature change. And we're going to use a calorimeter, to do that. So this is a calorimeter. This is a coffee cup calorimeter, which is most commonly used in chemistry labs. And so what it is we have 2 styrofoam cups that are put together, and we use 2 to try to increase the amount of insulation. It works okay. It works pretty good. And then we have a stir rod in here. You could either use a stir rod or you can use a magnetic stirrer. That's what we're going to use in our lab. You put some kind of top on it, and then you put the thermometer through it to measure the temperature. And then in this case, we're going to be specifically using aqueous solutions for our reactions or to measure that temperature change. So to do that, what we do is we are going to solve so the temperature that we measure in our solution is equal to the heat capacity or specific heat of the solution we're measuring times the mass times the change in temperature that we observe. And this whole thing is equal to the opposite of what happened in our reaction for the heat. So we'll talk about that in a second. So first thing I want to talk about is the specific heat or the heat capacity. So this is the amount of energy it takes to raise the temperature of a solution by so my delta T can be either, 1 degree Celsius or 1 Kelvin. And that is the same thing because both of these units are changing at the same rate. So if my temperature change goes from 25 degrees Celsius to 26 degrees Celsius, that's 1 degree Celsius. If I change both of these numbers into Kelvin, I'd have 298 Kelvin to 299 Kelvin. My delta T is still 1 Kelvin. So that's why those are interchangeable. So when I'm talking about specific heat, that could either be the lowercase c or an S for a specific heat. That's how much energy it takes to raise 1 gram of a substance by 1 Kelvin. And if we have molar heat capacity, that's 1 mole of the substance by 1 degree Kelvin or Celsius. So we're going to use that. So that matters a lot because if I'm measuring water, now water is very particular, and that's a good thing. But if I'm measuring water takes a lot of energy to change its temperature, which you maybe have noticed as you've cooked, like noodles or made ramen before, or like rice, right? It takes a while for water to heat up. And that's because it has a really high heat capacity. If you compare that to something like metal, right, you put some, like a baking tray in the oven, and it gets hot really fast. But if you put some water in the oven, it's going to take, or even on the stove, it's going to take a really long time for it to heat up because it takes a lot of energy to change the temperature of water. So if you're heating water by a lot, then you had to put a lot of energy into it to get that to happen. So that's where this C comes into. Now M here is the mass, and T is that delta T. So why are these the opposite sign? So if I have a reaction happening, let's say I'm making a reaction happen. The reaction, let's say it's exothermic, so it's releasing a lot of energy. So that if I know something's exothermic, then its delta H should be negative. But if it released a lot of energy, that temperature change is going to be positive. I'm going to see the temperature of my solution go up. So that's because my thermometer is the surroundings and my reaction or my system is being measured by my surroundings. So we're gonna find our heat of our solution using this equation, and then whatever we get, we're gonna switch the sign to find out what happened to the reaction, not what happened to the surroundings or the measurer. So keep that in mind. And then also a quick thing that I want to hit at real quick, the enthalpy of our reaction that we saw in our equations before, that's going to be the heat of the reaction divided by the number of moles of our reactant, of one of our reactants. Ideally the limiting reactant if that's applicable, but yeah, so we're going to take the heat we find in our calorimeter experiment, divide it by the moles of our reactant that we use to find the enthalpy of our reaction. So just to practice our Q equation, we're going to find out how much heat is needed to warm 250 grams of water from 22 degrees Celsius to 98. So I have Q equals Cm delta T from up here. I'm heating water, which the heat capacity is 4.18 joules per gram, and I'm going to actually use degrees Celsius instead of Kelvin, just because the reason I told you up here, times by 100, my mass is 250 grams, and then my delta T, I have 98 degrees Celsius minus 22 degrees Celsius, so that's 76. So when I multiply that all out, I get 7.9 times 10 to the 4 joules, or I can say 79 kilojoules, which is a lot of energy just to heat water from, room temperature almost to boiling. It's put in a lot of energy. We're not going to worry about that. We can calculate the molar heat capacity by turning this from grams to moles. So, FYI. So this is very similar to what we're going to do in our lab, so very exciting. So a student's going to mix 50 milliliters of a 1 molar HCl solution to 50 milliliters of a 1 molar sodium hydroxide solution in a coffee cup calorimeter. And the temperature goes from 22.1 to 27.5 degrees Celsius. Calculate the enthalpy change for the reaction in kilojoules per mole of hydrochloric acid, so HCl, assuming the calorimeter only uses a little bit of heat. So the total volume of the solution is 100 milliliters, and its density we're going to assume is 1 gram per milliliter, and that its specific heat is that of water. So where do we start? So I'm going to say the heat of my solution equals Cm delta T. So I have, my heat capacity tells me is 4.18 joules per gram. I'm going to do degrees Celsius. Now my mass. My total volume is 100 milliliters, but I need my mass in grams. So I'm going to use the density, which is conveniently 1 gram per milliliter. So I have 100 grams of solution. Convenient. So 100 grams is for my mass. Now my delta T goes from 21 to 27.5. So I'm going to say 27.5 degrees Celsius minus 21.0 degrees Celsius. Plug that whole thing in, and I get my Q of my solution is 2.7 times 10 to the third joules. Or we want it in kilojoules up here, so I'm going to divide by 1,000, so I get 2.7 kilojoules. Now my heat of my reaction is the opposite sign of heat of my solution, so I'm going to convert that into negative 2.7 kilojoules. Now I want to do that per mole of HCl. So I'm going to say I have 50 milliliters of HCl, and I want to get into moles. So I'm going to convert my milliliters. If you remember, a molar is a mole per liter. We're going to talk about that a lot in a bit, but as a reminder, it's a mole per liter. So I need to get my milliliters into liters so I can use molarity. So I have 1,000 milliliters per liter, and I use a 1 molar, so 1 mole per liter solution of HCl. So my amount of moles of hydrochloric acid is 0.050 moles. So I'm going to take my heat of my solution. So for enthalpy of reaction, I'm going to take my heat of my reaction divided by my moles of HCl. So I have negative 2.7 kilojoules divided by 0.050 moles HCl, and I get negative 54 kilojoules per mole of HCl. This is what we're going to do in our lab. Okay, so now I have 50 milliliters of a 0.1 molar solution of silver nitrate and 50 milliliters of a 0.1 molar hydrochloric acid solution mixed at constant pressure. And the temperature change goes from 22.3 to 23.11. The temperature increases from this reaction here. Now this is a double replacement reaction forming silver chloride, so fun fact. Calculate the delta H for this reaction in kilojoules per mole. So if the combined solution is 100 grams and specific heat is 4.18. So very similar. I hope you're pausing to do this on your own, but I'm going to plug in Q of my solution equals Cm delta T. So my heat capacity is 4.18 joules per gram degrees Celsius. Mass is 100 grams. Delta T is 23.11 minus 22.30 degrees Celsius. So my amount of joules, so my Q of my solution is positive 339 joules, or 0.339 kilojoules if I divide by 1,000. So my Q of my reaction is going to be the opposite sign of that. So I'm just going to put a negative 0.339 kilojoules. Now I'm going to find out how many moles of sodium nitrate I have. Or I mean silver nitrate. So I have 50 milliliters. And I'm going to convert that into liters. So 1,000 milliliters per liter. Now my molarity is 0.1 moles per liter. So when I do this, I have 0.005 moles of silver nitrate. So to find the enthalpy of my reaction, I'm going to do my heat of my reaction divided by my moles of silver nitrate. And I have negative 0.339 kilojoules divided by 0.0050 moles of silver nitrate. So when I plug all that in, the heat of my reaction is negative 67.8 kilojoules per mole of silver nitrate. Okay, cool. So this is what we're going to be working on in our lab, and then we're going to move on soon to talk about other ways that we can find enthalpies, less using experiments and more using other types of data.